All right, so last time we were talking about the early theorists and their ideas about what an atom is. Now we're going to talk about the two really important contributors to the modern atomic theory. So Thomson is our first one. And Thomson did a cathode ray experiment. So I have a video that I can show you what a cathode ray is. This is the best video I could find. And I'm just going to mute it so I can talk about what's going on in there. And I know there's a strange band there, but just ignore it. Alright, so a cathode ray is basically a tube with no matter in it. It's a vacuum. And you're really running electricity through it. So you've got a positive end and a negative end. And it was really baffling people about what was conducting the electricity since there was nothing inside the tube. So once you, and he's going to turn it on. So once you turn it on, you're going to see this green beam right there. That's called the cathode ray, and they don't know what this is made out of. Okay? You tried it with different elements, you still got the same thing every single time. So they're trying to figure out what this was. So what he ended up doing was applying a magnetic field to it. And then he would just basically take a magnet up to it, and he's about to show you in just a second. He would take a magnet towards that beam and push down on it. So once you take the magnet on a certain end, it actually, you can see right here, it's being deflected, so it's being repelled. Now if you flip it over, if you flip the magnet over and then apply the magnetic field again, when you have a different pole, it's attracted. So if you can see that beam right there, it's actually going up. That tells us that this beam has a charge. And because the positive end would attract that beam and then the negative end would deflect it or repel it, we had to conclude that this beam was made of negative particles. Now what he also found, using that angle of deflection, so the angle at which it either goes up or down, he found out that it is 2,000s, or it's much, much smaller than a hydrogen atom. So if it's much, much smaller than a hydrogen atom, that had to mean that inside an atom there were smaller particles. So Dalton said that atoms are indivisible. That's not true. Thomson discovered the electron, which is a negatively charged particle, which is part of the atom. So he came up with a model for the atom, and he called this atom, or this model, the plum pudding model. And basically, because he found a negative charge, and everybody knows, or everybody knew that atoms were neutral, that means that there has to be a positive charge canceling out that negative charge. And since no anode rays were found, so the cathode rays had beams of electrons, and there was no positively charged rays, they had to conclude that the positively charged particles were too big to move from place to place like the electrons. So the electrons had to be really, really tiny compared to the positively charged particles. So he said it looked like plum pudding or bread pudding or a chocolate chip cookie, basically. So inside of your atom, you have these little negatively charged particles right here. And then everything else is the positively charged protons, or positively charged particles. So that's what he came up with after he discovered the electron. So now we're going to talk about Rutherford's experiment. So Rutherford did the gold foil experiment. Okay, and basically, he took a radioactive substance, plutonium, which is actually some pretty dangerous stuff. That's the stuff we use in atom bombs and hydrogen bombs. And this plutonium emits particles, which are positively charged particles. They're called particles, which are called alpha particles. Okay, and because it's radioactive, it just constantly emits these particles. So he took the plutonium, and basically the particles were forced to go into a beam, and he beamed it at a thin piece of gold foil, very, very thin piece of gold foil. Now, alpha particles, if you take a piece of paper, they can actually be deflected by a piece of paper. But what he actually found, because he had a device to measure the amounts of radioactivity around it, which alpha particles were radioactive, most of these particles went directly through the gold foil. Okay, most of the particles went directly through. And then he saw that every now and then there would be a beam being either bounced back or deflected at an angle. Okay, so some of these went through at an angle. So basically, his experiment was to take alpha particles and beam it at gold foil. And then what he observed was most of them went straight through, but then some of them got deflected around it. So what can he conclude from this? Well, since these positively charged alpha particles would pass through most of the time without being deflected, they would just go straight through, he said that atoms have to be mostly empty space, which is very different from Thomson's theory. And then he also said that some particles were deflected. He saw that. So some of them would bounce at an angle or bounce straight back. So he said that they must have passed something that was very small and positively charged. Because remember, positive and positive, they will repel each other. So he said atoms mostly empty space, and then he also said that the positive charge has to be very small. There has to be something very small that's positively charged inside the atom. So this led to a new model of the atom. We call that the nuclear model. So with his experiment, he said that the positively charged particles were inside something called a nucleus. And then the negative electrons have to float around the rest of the atom's empty space. So Thomson said that there was a very massive positively charged particle, but Rutherford said no, it has to be very small, located in the center, and the electrons have to be orbiting around it. All right, now there are several scientists who actually contributed to the model of the atom, like Chadwick discovered the neutron. There's Millikan, who discovered the charge of the electron. But we're just going to talk about the main people who helped change the theory as we go through time. All right, so that concludes this podcast, and I will see you in class.